So I just would like to remind where we are and what we have done and what you have done up to now, to then introduce the next steps of our work. So what we have been doing is looking at the, so we have to solve the design of the energy system of EPFL, which means that we have been looking at the list of buildings that were in the campus. From there, I guess that every one of you have been assigned a characterization of each of the building, and that you have been able to identify what were the needs of each of those buildings that were characterized by a model that defines as a function of the time at which we are, as a function of the presence of the people, as a function of the quality of the building. What are the needs of each of those buildings, which in your case have been even improved because you were doing a look at the the possibilities of reducing the amount of heat that is needed to the building. And what we can say is that as soon as we are able to characterize what we have been defining as the heat of a building in a given state at a given time, we were able to say how much heat will be needed in each of the distribution systems that are connected to the buildings. So it means that we will be able to know what is the amount of heat that needs to be supplied by the district heating system that is here, after having made some heat recovery as it is explained here and here. Okay, so it means that we have the possibility of increasing the efficiency of the system by adding heat recovery systems. We have to control the air that we are going to supply. We control the heat distribution system inside the buildings. Okay, so all those elements have been calculated, and from there, then we have identified the different possibilities of how to supply the heat that we have been calculating for the buildings. And we have been looking at the different units that can be used in order to supply this heat that we have characterized by a unit, and the unit is expressed by a certain amount of heat that it is going to supply a given unit. So we have identified different levels for the heat pumps. We have identified a steam turbine, a gas turbine as well as being a unit that is able to supply a certain amount of heat to one of the distribution systems. Okay? And we have been writing an equation that is going to tell us that, and this is the equation that is here. I'm going to use the green part here. So this equation here is going to tell us the amount of the amount of heat that needs to be distributed to a distribution system at a given time is supplied by using a given unit U at a certain level, FUT. So it's the level of usage of the unit U at time t. Okay, and we write a balance. So this is an equation that is going to say that the level of usage of the different units that are able to supply a given amount of heat to the distribution system D at time t will be calculated as such that it will satisfy the needs of the distribution system. And I have another question here, this one here, that is telling me that the amount that I need in the distribution system D is in fact the amount that is asked by all the buildings that are connected to the distribution system D at time t. Okay, and this is the sum. I can also see that this sum is going to define a flow that it needs to be distributed in the distribution system D at time t, multiplied by the Cp, multiplied by the temperature difference between the supply and the return temperature of each of the distribution systems. And I remind you that in EPFL we have two different types of distribution system, one at high temperature and one at low temperature. So what we have also seen is that I will have to account for the fact that when I'm supplying a certain amount of heat by the unit U, sometimes, no, always, I'm going to consume a resource or a distributed energy. So for example, when I'm using, I'm supplying a certain amount of heat by a heat pump, then I know that I'm going to spend a certain amount of electricity in the corresponding compressor, okay? Which is going to be calculated by saying that the amount of electricity of the unit U at time t is equal to the heat that is delivered by the unit divided by the COP of the unit. And we have as well seen that the COP was calculated as a function of the temperature of the distribution system and as a function of the temperature of the resource that we have. So for example, the lake that is available. Okay, so which means that at the end I will be able to write another balance, which is the balance of the electricity consumption. Okay, so summarizing, I have here the supply of the heat by the different units that have been calculated at a given heat supply level that will be multiplied by a certain level of usage at the time t. I have the balance of the heat that is needed at the temperature T in the distribution system D. I'm going to write another interesting equation. I'm going to say that if there is heat available at high temperature in a distribution system by a heat cascade, so by indeed a heat exchange, if it is supplied at higher temperature, I can always use it at a lower temperature. So it means that I'm going to write, therefore, an equation that is written like this. The amount of heat that is coming from the higher temperature level of the distribution system, and I'm writing this because it's possible that I will have will have more than two district systems if you want to optimize it, okay? The amount of heat that is distributed from the highest temperature is equal to the amount that is needed at the given in a distribution system D minus what is needed in the distribution system D. And the remaining amount is the one that is sent to the lower temperature level. So knowing that I have the equations that makes the links between the heat that is supplied and the electricity that is consumed, and this is calculated for the moment by a simplifying equation that is based on the calculation of the theoretical COP, which is here with temperatures in Kelvin, don't forget. Okay? And those temperatures here are the mean temperature in terms of these are the logarithmic mean temperatures that I'm going to multiply by a Carnot factor. The Carnot factor is representing the quality of the technology in the model. So I know that the technology will follow the rules of thermodynamics, meaning that the COP will be a function of the sink and the source temperature, mean temperatures. But most probably they will not be as good as the maximum theoretical amount, because this is the maximum theoretical amount. I'm going to perturbate or to represent the non-ideality of the technology by using a factor which is the Carnot, what I'm naming the efficiency with respect to Carnot factor of 55. The value of 55 is just because I know that engineers are able to design systems that reach the 55 value here. Okay? So this is really heuristic, and this is just an assumption. The advantage of using this representation is that if the temperature outside is changing, or if the distribution temperature in the building is going to change, the sink temperature here will change, and therefore I know that the electricity will be perturbated, and therefore by using this representation, I will be able to at least represent what the thermodynamics, what I know from the thermodynamics. Okay? Now, of course, the value that I'm going to use here, that should normally, if I well remember, I have, no, I don't have it here. So, that should normally be coming from the model of a heat pump with a given refrigerant, with given pressures at the evaporator and with given pressures at the condenser, with given sizes for the heat exchangers. That should normally be the way you should model the heat pump, will be summarized or simplified by having this value here, the COP equal to the efficiency with respect to the COP, which is 55%. Okay? So for the moment, it's just a trick that allows me to solve the problem in a very fast way. So the advantage of it is that I have a COP that is a function of the temperatures at which of the different systems. So I have a different COP if I'm in a low temperature distribution system or in a high temperature distribution system. Okay? But it's just an assumption, so don't forget that for the moment it's a simplifying assumption. The advantage of it is that now I can make a link between the heat that is supplied and the electricity that is consumed. So now I can also write an electricity balance here, and the electricity balance includes the contribution from the different units. And I'm also considering the fact that it's possible that I will have units that are going to produce electricity. For example, here I have a gas turbine for the moment that is producing electricity if it is operated. So it means that in this case, some of the unit will consume, and some of the unit will consume electricity. Some of the unit will produce electricity, and at the same time they will, by this equation here, this one, I will also have the link between the electricity and the heat, both in terms of cogeneration or heat pumping. Okay? Is it clear for you, this? Yeah? Okay. And similarly to the amount of electricity that is consumed, I will have also the possibility of calculating how much resource is used, for example, in a gas turbine. So in the gas turbine, I will have a certain amount of mass flow of a resource, natural gas in this case, which will be related to the amount of electricity that it is going to produce. Okay? That is going to be associated as well to the amount of heat that it is going to produce. Okay? So officially, if I'm adding here an equation, I would consider that the electricity produced by the unit U at time t is equal to the factor of utilization of the unit times the times the electrical efficiency times the mass flow of the resource times the lower heating value of the resource. Okay? And I would say also that the heat that is supplied by the unit is equal to the multiplication factor times the thermal efficiency times the mass flow of the unit times the lower mean value of the resource. Okay? So it means that as soon as I have the electrical efficiency of the cogeneration unit and the thermal efficiency of the cogeneration unit, I am able to make a link between the flow of the resource that we have here, the electricity that will be supplied, and the heat that will be supplied. And everything depends on the level of usage of the unit. So what I'm going to do is that I'm going to use a nominal condition which defines, for example, the typical flow or the best flow of gas in the gas turbine when the gas turbine is used in nominal condition, that I will multiply by a multiplication factor which is the level of usage of the unit, okay? So, which defines the part load of the operation of the unit. So when I have done this, then I will have the possibility of calculating the performance of the unit. And one of the performance of the unit is the operating cost. Okay? So up to now, I was looking here at something which was depending on t, so on the time. Okay? And if I want to know now how much energy I'm going to, how much I have to pay for operating the system over 1 year, then I will have to define the integral of the amount of energy that I'm going to spend over 1 year. And this is now saying that, okay, officially we have, it is a little bit more tricky than just 1 year, because in reality, if you, as we are going to decide what is the size of the unit, we do not have to look at 1 year, but at the lifetime of all the buildings and the equipment that we are going to buy. Okay, so officially we are going to look at 25 years of operation. We are going to simplify this by saying, okay, let's look at 1 year, and then we have been, and this is what you have done last week. We have been also considering that a 1 year of operation can be represented by some typical days, okay? Which then allows me to estimate the cost, so in Swiss francs per year, of 1 year of operation as being made by the sum of the typical time over, and I have to consider the duration of each of the typical time, multiplied by, and then there are two elements here, the specific cost, so this is, for example, the Swiss franc per kilogram, okay, that I'm going to multiply by the flow, and this is kilogram per second, and that I'm going to multiply here by the second per period. So it's second per year, in fact, huh? Yeah. Okay? And I have to do this, to take this cost, specific cost, for each of the units, each of the resources that I'm going to consume, but I'm going also to look at the electricity here that I'm going to buy, and probably as well, if I have enough PV panels, there will be some cases or some time during the year where my system will be in a position of exporting electricity. The same when I'm operating the gas turbine, it's possible that amount of electricity produced by the gas turbine will be higher than the amount of electricity that I need, and therefore I'm going to export it. And obviously, I will not get the same price when I'm buying electricity or when I'm exporting electricity. So the utilities will charge me a certain value for transporting the electricity, and therefore the amount of electricity that the price at which I'm buying the electricity will be higher than the price at which I will be able to export the electricity. Okay, and that's why there are two costs, there are two prices: the price at import, and this is Swiss franc. I'm going to use per kilojoule, and here I will have the same in Swiss franc per kilojoule. Okay, so those are specific, so those are prices, and something that is in fact also written in the formula is that it's possible that the price is changing with time. Okay, and if you have access to the electricity market, the prices can be very different from one time of the year to another one. Okay, if there is a lot of wind blowing and if there is a lot of electricity produced by the PV panel at the same time, the cost is going to drop. If there is no wind, if there is no sun, and a lot of people need electricity, then the price will be very high. But it can be very, very different. So it might happen on the electrical market. There are periods in the year where there is too much electricity. So it means that the people buy electricity at a negative price. Okay, so it might happen that the market is going into this direction. So that's why the electricity price that we are going to use can be a function of the time at which we consume. Okay, so it's a specific price. I have written per kilojoule. In reality, you will have to just be careful on the units that you are going to use. So you can also have prices in kilowatt hour. I have also used the resource in kilogram. It can be also per kilowatt hour or per megajoule or per cubic meters. So you have just to be sure that you are using the right units for calculating the formula. And the last dimension that I have added here in the operating cost is this term here. And this term is related to, so it's an operating cost, it's the amount that you have to pay for the maintenance. Okay, the maintenance is the fact that we have heat pumps that use compressors. You have rotating machines, and if you have rotating machines, then you have to be sure that they will continue to rotate, and so you have to make a maintenance. Okay, add some oil in the bearings. Okay, just to be sure that everything runs well. Okay? And this then defines a cost that you will have to pay each year for someone to come and to make the maintenance. Okay? So, having said this, then I have defined the annual operating cost, and so you have been looking at the way to define define the temperature, the time intervals that are characteristic of the operation of the EPFL. So I will just skip this part. But just to remind you that at the end you have been able to define the list of time during which that will allow you to represent 1 year of operation. So now we still have a question, and the question is, what are the best operating conditions first? So it means that at each time in the system, I will have to define what is the best value of the level of usage of each of the units. Okay? which will allow me to minimize the, for example, the operating cost. But in addition to this, I will have to consider that I have to buy the units. So it means that I have to make an investment, which means that at the same time I'm calculating the amount of the operating cost each year. I will have also to calculate how much I will have to reimburse for the investment that I have made. Okay, and for this we have seen that there were formulas that were allowing me to calculate what will be the cost of a heat pump if I know the size of the power of the compressor. What is the cost of a heat exchanger if I know the size of the heat exchanger area? So it means that now for each of the unit I'm able to calculate how much the unit will cost. The problem is that I do not know exactly, because it will depend on the way on the services that each of the unit will deliver. I'm not aware about what is the good size. Okay, and the size at the end will be a function of the maximum level of usage of a unit. Okay, and as soon as I have the size, then I know that I know how to calculate the investment, which means that I will be able to calculate something which is named the capex, so the capital expenditure, which is the amount of money that I have to pay to buy all the units that I have in my system. Now I'm going to make a simplification. I'm going to linearize the curve, because here the cost curve has typically a form like this. So the cost is equal to, I just write it once again, just so that you remember. So there is an index, okay? Then there is a purchase cost, to which we apply a bare module factor, let's name it FBM, that corresponds to the connection of the unit. And then we have an exponent here, which is the size of the unit divided by the size of a unit of reference with a given exponent for the unit. Okay, so this is the typical formula that we have to estimate the cost of a unit when we have when we know the size of the unit. And this is a formula that has is nonlinear. So you can see that we have an exponent here, and this exponent is typically between 0.6 and 0.8. Okay, so it's not 1, which means that the cost is not a straight line. Okay. Now, if I want to go fast in making my calculations, I would like to avoid having nonlinear terms. So what I'm going to do now is that I'm going to linearize the unit, the cost formula, and I'm going to replace the blue curve by the red one, which is the straight line. Okay? And the straight line has two components. There is something which is related, which is named the fixed cost, which is here, that I'm going to associate to the existence of the unit. I'm going to use as well a new decision variable, which is the YU here, which is going to tell me that if the unit is used, then the integer variable y will be equal to 1. I select the unit, and in this case I will have to pay a fixed cost, which is the fixed cost that I can read here. Okay? And then I'm going to say that the cost of the unit, U, will be approximated by something which is therefore a fixed cost plus a proportional cost multiplied by the size. Okay? And I can calculate the slope of the red curve by using the 2 points that I have here. So I can calculate this point, I can calculate this one, and I'm sure that you know how to calculate the two coefficients of a line that is passing via 2 points. Okay, so really easy to do. And now my cost formula is becoming a linear function that has two terms, in fact, in it. The decision of using or not the unit and the size of the unit. Okay? In fact, I have done also something which is an engineering action here. Because to do this, I have to choose the 2 points here. Okay? And I'm choosing 2 points by defining the minimum and maximum bounds of the validity of the linearization. So I'm going to say that this cost function is valid, provided that I am between the min and the max bounds that I have obtained, that I have decided. So what does it mean? It means that I'm not going to use the same formula for calculating a heat pump of 1 kilowatt, that is just used in your car, and a heat pump of 5 megawatts, that is used in EPFL. Okay? It's just to be sure that we are in the good order of magnitude, and it defines the validity of the model that we are using. So I think that this is a message that is very important. When you state a problem, you can always state a problem that is a mathematical problem. Okay? But a mathematical problem has no value for you. The mathematical problem plus parameters that make sense for you are the problem that you need to state. Okay? So what my other message here is that as soon as you use a mathematical formula, be sure that you are using the mathematical formula in the zone for which it has a sense. Okay? Otherwise, you can go into very strange results. Okay? So the message is, don't forget the minimum and maximum bounds to define a problem that makes sense. Yeah?
Can you repeat what the third factor in the cost function was? The handwritten. The one by hand?
This one?
No, the one you wrote with the green by hand.
This one here?
Yeah.
Okay, so this is the official value or the official mathematical formula to estimate the cost of investment of the unit U. Okay? That you obtain by looking in a book where, and then you will have, in the book you will find this value here, which is the purchase cost of the unit U. Okay? And in the book you will also find the bare module, what we name the bare module factor, which is the factor that applies to the purchase cost, and it is going to define the fact that you have to plug the unit in the system. So you have to draw pipes, you have to make a foundation, you have to add a control system, a safety system to it, and it multiplies the cost of the purchase unit. Okay? So this value is given for a reference size, that is here, okay, of a given unit. And this term here, which has an exponent which is gamma, okay, which is the scaling factor, allows to consider the fact that we know that a big unit costs less than a small one per unit of service delivered. Okay, so for example, installed power. Okay, so this is an observation, in fact, from the market. And the last term that is here, sorry. So the last factor that is here is the index factor, which is going to consider the fact that, well, the values that you have obtained here, this one and this one, are in fact all obtained for a given year of reference. if you are using a book, it's the date at which the book has been published. Okay? And you can find in another book, the computer, the chemical engineering journal, for example, the value of the index of today. So this is the index of today. And the index of today is going to tell you that if you have bought the unit in 2000, it has cost 10,000 Swiss francs. And if you buy the same today, it would cost you 12,000. Okay? And the 1.2 is in fact the ratio that we have here. Okay? Just an additional remark. So this is a general formula for one unit, and in reality, so don't forget that here I'm doing the sum of all the units. Okay? And I must admit that if the unit is a heat pump, in fact, the cost of a heat pump is equal to the sum of all the unit in the heat pump. Huh? Heat exchangers, valves, compressors. Okay? Yeah.
So maintenance is included in these coefficients?
No, the maintenance I have put it in the operating expenses, okay? But you can find the value of the maintenance in the same book. Because typically they tell you, okay, if you pay so much for investing, for this type of unit, for example, a compressor, it's so much of maintenance, for the heat exchanger is so much, and the reason for, and there will be a difference between the two, because one is rotating and has high maintenance cost, while the other one is going to be have some fouling, so it needs to be cleaned, but perhaps once every 4 years. Okay, and in this case, you have to, the cost will be lower. Okay, and for those, if you take the values in the books, it's always interesting to also use an index for the value of the maintenance. Okay, just because the index of the wealth value of the society is changing, and so the manpower cost is going to change as well. Okay? Okay, so now what I have is the operating expenditure, the capital expenditure, and I have as well the possibility of calculating the environmental impact cost. So what does it mean? It means that if I'm using the unit, and if I'm using a given resource, I have calculated the flow in the resource, that is going to be associated, this can be associated to a given amount of carbon dioxide emission, for example. Okay? And I can add to this carbon tax. Okay? The same, I have calculated the amount of electricity that is produced. I can therefore associate the amount of carbon dioxide emission that is emitted when I'm buying electricity from the grid. Okay? And this coefficient is a function of the time. Because if the sun is shining everywhere in Europe, then there is a low level of carbon dioxide in the electrical grid. If there is no sun and everyone needs electricity and that's only the coal power plants in Germany that are operating, then I will have a big carbon dioxide emission in the grid. So it means that the coefficient that is here, the coefficient that is here may be a function of the time. And there is one website on which you can go and see the flows of carbon dioxide in the exchanges between the different countries in terms of the electricity, and you can find a value. I think that you can obtain the hourly value. So the name of the website is SOA. There you can find the CO2 emissions associated to every at every time for the electricity that is supplied. And therefore, I will be able to calculate also the environmental expenditure, which is the price to pay related to the emissions that I'm creating. Okay, it will be then affected to a tax that the people will have to pay. Okay? Yeah.
Why are we subtracting the amount that we supply to business?
Sorry?
Why are we subtracting the electricity that we supply to the grid?
Yeah, and this is a good question. It's because I'm making the assumption that when I'm supplying the electricity to the grid, I'm going to ask the grid to supply less. Therefore, the related carbon dioxide emissions for the amount of electricity that is not needed from the grid will have a negative value. So it means that I can have a reward from the fact that I'm selling electricity to the grid. But at the same time, I have to pay for it, because my model is going to tell me that if I'm running my gas turbine to produce electricity and if I'm exporting, then in fact, I will emit carbon dioxide at the level of the gas turbine, but I will have a reward because I'm exporting to the grid. Okay? Yeah.
What about the environmental impact related to the production of the units that we have to invest?
That's a good question. So one could also add this one. So for the moment, I was using it. I was adding this dimension in the cost. So the operating cost. In reality, if I want to calculate the total amount of carbon dioxide that is emitted by the system, I will have also to associate to each of the units. So it means something which is related to the size of the unit. Okay? Something that is related to the size of the unit, I would have to consider the amount of carbon dioxide emissions that have been emitted for producing the unit. Okay? But in reality, I will not have to pay a tax for it. Or at least for the moment, the people do not pay for this tax. They pay for the tax because the price is going to be increased, because the people have to, the one who is building the heat pump is going also, will have to buy the energy that is needed for producing it, and will have to pay the tax. Okay? But you're right, so if I want to know how much carbon dioxide is emitted by my system, I should in fact consider the amount of carbon dioxide that is emitted by producing all those units, including the refrigerants that I'm going to place in each of the heat pump. I should officially also consider the fact that when the unit will be dead, I will have to dismantle it, and this might also consume energy. Okay, and therefore emit carbon dioxide. And I have to be sure as well that if I'm using a refrigerant that has a global warming potential, it will not be released when I'm going to dismantle the plant, but it will be treated. Okay, so it means that you will have to also consider this. But now if I'm summing up all what we have done, and we have, is that I have the possibility of calculating the total annualized cost, which includes the operating expenditure, the capital expenditure, and the environmental impact, the no cost related to the emissions. I'm going to add a constraint that is going to tell me to make the link between the size and, which is FU here, and the existence of the unit, the YU that is here. Okay, so that I will have something that is going to extinct or not the unit if it is used or not. So it's a 0-1 decision. And I can even be a little bit more smarter by saying that if the unit is used, it has to be used at a certain level during its operation. So it means that it's possible that I have bought the unit, so the unit is there, but there is no interest of using it. So I can be in a situation where I will decide to not use the unit at a given time, okay, but still have it in the list. Okay, so it means that it will introduce a cost, right? So I have the models, I have the balances that have been added to the system, okay? In terms of resource, in terms of heat, and in terms of electricity. So I have the link with the demand by this way here. I have the link with the resource. So I have a list of equations that allows me to calculate what are the flows that I will have in the total flows that I will have in my system. And therefore, the goal is now to calculate the level of usage. So that's what is written here. I will have to calculate at which level the unit is used at a given time, if it is used or not, if I have to buy the unit, and if it is, if I do the investment, then at which, what is the size, the corresponding size. What will be, therefore, the electricity that I'm going to export, the amount that I'm going to import, the amount of resources that I'm going to buy, because it has an impact on the cost. And I would like to have all those values defined in such a way that I will be smart and I will minimize the total cost. Okay? So by saying this, I have defined an optimization problem. Okay? So one could decide that the easiest way is just to fix the value of some of the well-chosen variables and then look at what are the values of the other. Okay? But it's not so easy. So what we are going to do now, and this will be the subject of the next hour, is how do we state this optimization problem. So for the moment, I have just declared that I would like to find the values to minimize an objective function. Okay? Do you have questions? If not, then we make a 15-minute break and then, oh no, let's say 10-minute break so that we can end up at noon and we start again. Okay?